Hello, Calculus 3. Today we're talking about Lagrange multipliers, or as I like to call it, turning hard calculus problems into hard algebra problems. So I hope you have your algebra juices all flowing, because this will be even more algebra than normal today. All right, but first, let's start off with the Jesus Creed. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. So, this is our main thing that we're doing today. This is why we can do it. So, if we have two functions that are continuous and differentiable, and suppose that f, when restricted to points on the curve, gxy equals 0 has a local extremum at the point AB. Your book uses x0 and y0. So if you're following along in your book, um, anytime I'm going to use AB because I like to avoid subscripts when I can, but the book likes to use x0, y0. So local extreme at the point AB, and that the gradient of g at AB is not equal to 0. Then there's a number lambda. So this is the Greek letter lambda, which is written like that. Like you go a downstroke, diagonal, and then there. Pronounced like lamb. Duh. Lambda. Spelled more like this though. Lamb. Lambda. All right. So lambda, which is called the Lagrange multiplier, for which remember this is the gradient. So the gradient of f is equal to lambda times the gradient of g. Okay. Also requiring this. So there's really two equations going on. You've got we're gonna take this optimization problem where we want to find a local maximum or local minimum, hence the word extremum here. And we are going to turn it into an algebra problem by setting gxy, that's our kind of our what's it called, our constraint, or set that equals 0, and then we're going to solve this equation for some unknown lambda. So here are problem solving steps. So f is the objective function, g is the constraint function. Question like, are we maximizing, are we minimizing? Set up a system of equations. So this is right here, this is a vector equation. Which might give us 2 or 3 equations depending on how many and what dimension we're in. So you get an equation. You're going to get an algebra equation for I, J, maybe K, depending on how many dimensions you're in. In this case, I'm talking 2 dimensions. So right now, we're not worried about that. We'll get to that later. So this set of 2 equations here is really going to be 3 equations in our first couple examples. Um, and then we'll solve for A and B. There might be multiple solutions, and there might just be one solution. The largest f of AB is the maximum, the smallest f of AB is the minimum. Warning, this technique only works when f and g are differentiable. So check the endpoints of g to be safe. Okay? All right. Let's get started then. So start off nice and easy. I think I meant for that to be a minus, perhaps. Yeah. That's supposed to be a minus. That's just one big fat minus now, okay? All right. Well, we will look at what do we need to do? We need to find the gradient of f and the gradient of g. So the gradient of f is the x derivative. So 18x plus 36y minus 18i. The gradient with respect to y would be 36x minus 8y minus 8j. Gradient of g is 3i plus 4j. That's the easier one. So then we have, we set these equal to each other with a lambda. So that means that we're just kind of compare the I components and the j components that have a lambda and the same lambda between them. So it's going to look like this. That means that 18x plus 36y minus 18 equals the g part, but with a lambda, 3 lambda. And then we have the j equation. So then we get 36x minus 8y minus 8 equals, and then over here is 4. So it equals 4 lambda. And then we have g of x y equals 0. So then bx plus 4y minus 32 equals 0. And now this becomes algebra. It's only algebra from here on out. Even though it's messy and difficult algebra, we can always reassure ourselves it's only algebra. So we need to solve for x and y and lambda. So we have 3 unknowns, we have 3 equations. In this case, this is a nice example because everything is linear. Therefore, we will only have either one solution, infinite solutions, or no solution. So let's get to work. Now, there's a couple ways to do this. I could show you, this is an example in your book. It's a checkpoint in your book, so you don't get to see the answer. But we could do this by hand where we you try to get zeros. You try to take you could solve for different things. So if I don't care what lambda is, so one technique is to solve for lambda here and here, and then just set these two equal to each other, and then you've kind of gotten rid of the equation and got rid of lambda. So I'll do that first. I'll do that technique first because that's kind of the way the book likes to do it. And then I'll come back and do it my way. Okay, so I intentionally put a blank slide beneath here, knowing I need some room for algebra. And so solving for lambda in the first one, I get, so I'm going to call it, think about these equations like 1, 2, and 3. And when you're doing algebra with 3 equations at the same time, you always got to kind of keep them together when you can. So the first equation I'm solving for is, well, I'm taking the first equation divided by 3. So I get 18 divided by 3 is 6. 6x plus 12y minus 6 equals lambda. That's kind of equation 1. And then equals, solving divided by 4 here. Well, 36 divided by 4 is 9x minus 2y minus 2. And look at that. It's such nice numbers. It's like this was originally given to us as a nice little example. So I'm just going to rewrite that without the lambda. So then remembering that this is like a combining of equations 1 and 2. All right, so equation 3 is still true. So we'll bring that back in a bit. So that means let's simplify. Let's move our x's to one side and our y's to one side. So that means that we have, let's move everything to the left side, just like equation 3. So we'll move subtract 9x over and I get negative 3x. Add the 2y to both sides and I get 10y. Then I got a minus 6 here, a minus 2 there. So add 2 to both sides, I get minus 4 equals 0. And then equation 3 is still true. It's 3x plus 4y minus 32 equals 0. Well, looky here. If I happen to just add, so these are my two equations now. And I have now two equations and two unknowns. So I'm moving in a simplifying direction. And it was good to kind of like leave lambda behind because that's a number I don't really care about. I only care that it's the same from equation 1 to equation 2. So leaving it behind is a good technique. And now if I add these two equations together, the 3x and the negative 3x will cancel out. Now I'll be left with 14y minus 36 equals 0. Well, looky there. So then I can divide that by 2. So 7y, 36 divided by 2 is 18. So y equals 18 over 7. And then x, let's see. X is it's the simpler of the two. Neither of them is simple. All right, well, let's just plug that into equation 2 here. So 3x plus 4 times 18 over 7 minus 32. No, yeah, 3x minus 32 equals 0. So then 3x equals 32 minus 4 times 18 is 40 plus 32 is 72 over 7. Oh my. All right. So at this point, maybe we'll pull out a handy dandy calculator. And everything was looking nice until we got to the fractions, huh? So then I do 32, subtract 72 divided by 7. And then I get basically like 21.7 divided by 3. And so x is about 7.23, which is, so x equals, as a fraction, it's 152 over 21, which is approximately 7.238. All right. Now, going back to our original question, here was our function. There was the constraint. And so we got only one answer. So that answer might be the maximum, it might be the minimum. Let's plug in, if we were in a situation where x and y had to be positive, then we would plug in the endpoints of this. So for instance, plug in, so we'll plug in our point 7.238, and then what's 18 over 7 is roughly 2.57. So y is approximately 2.57. So then we'll plug in to this are 2.57, 7.238, and we'll plug in the endpoints of G, which would be like x is 0 and y is 8. We plug in also when x is, say, 32/3 and y is 0. So plug all three of those in and see which one is the maximum, which one's the minimum. Okay, well, any questions about that? That's a funny thing to say. You guys can't ask questions. This is a video. So I'm going to end the video here, and then I'll start a next video for the next example.